Welcome viewers to the last segment of the fifth lecture for the online series of lectures for the course of Algebraic Topology 1. Towards the end of the previous segment, we proved the first step for the fundamental theorem of algebra, which is our theorem 5, where we dealt with this continuous function f from the unit circle to itself, given by f of z is equal to z to the n, where z is a complex number of unit modulus. We have shown that the induced homomorphism of the continuous function, denoted by f star, which is a map from the fundamental group of the unit circle with reference to this base point b0 to itself, is injective. Okay, this is what we have done in the previous segment. Now, in this segment, we proceed with the second step of the proof of fundamental theorem of algebra. At this stage, we first show that if G from the unit circle to the punctured plane is the map given by G of z is equal to z to the n, although they appear to be the same, f and g, they are not the same function because f is a map from the unit circle to itself, whereas g is a map from the unit circle to the punctured plane. Okay, and we see how they are related. If j is the inclusion map of the unit circle into the punctured plane, if j is the inclusion map, okay, then one immediately sees that j composed with f is precisely g. Okay, this is our equation number 1. Now, in terms of the induced homomorphism at the level of fundamental groups, at the level of fundamental groups, one finds, or the above equation reads, J star composed with F star, which is of course J composed with F star, which is G star. Okay, this is our equation number 2. Right? Now, the point to note is that since S1 is a retract of the puncture plane, we have seen it earlier, right? By lemma 1, the induced homomorphism corresponding to this inclusion map J is injective. Okay, right? And we proved earlier in step 1 that F star is injective, right? And we proved in step 1 that F star is injective, and the composition of the injective maps is again an injective map, which means that G star is injective, right? G star equal to J star composed with F star is injective. Okay, good. So, what did we prove? Let me erase this bottom part. We proved that for G from S1 to the punctured plane, the induced homomorphism which is a map from the fundamental group of the unit circle with reference to a given base point B0 to the fundamental group of the punctured plane with a reference to the base point G of B0, right, is injective. This is what we have proved so far. Okay. Now, since the fundamental group of the unit circle with reference to the base point B0 is non-trivial, in particular, this is isomorphic to the additive group of integers, and G star is shown to be injective, right? This induced homomorphism G star cannot be trivial. So, G star injective plus the fact that this guy is non-trivial implies that G star is non-trivial. What does it mean? What does it mean by a homomorphism being non-trivial? It means that the image of this map G star here cannot be just the identity element of this group. Okay, so G star is non-trivial, which means that image of G star is not just the identity element in this fundamental group of the punctured plane. Okay? Alright. So, by lemma 2, then, for this map G, one can invoke lemma 2 and see that G is not null homotopic. G is not null homotopic. Okay? Good. So this is what we needed to do in this second step. We needed to prove that G is not null homotopic. Now in the third step, we prove a special case of fundamental theorem of algebra. Okay? We start with a given polynomial equation, x to the n plus a n minus 1 x to the n minus 1 plus all the way up to a1x plus a0 is equal to 0, which we number by equation number 3. Okay. Then we assume, so this is the reason we are calling it a special case of the fundamental theorem of algebra. We further assume that the following holds. The mod of these complex coefficients, mod of an minus 1 plus all the way up to mod of a1 plus mod of a0 is bounded by 1. Okay, we want it to hold. Now we need to show that. We now need to show that equation 3 has a root lying in the unit ball V2. Okay, this is what we are going to do in step 3. Let's prove it. We proceed by contradiction. Assume that there is no such root. Assume there is no such root. Okay. Then we can define a map. Then we can define a map K from the unit ball to the punctured plane as follows. K of z is equal to z to the n plus an minus 1 times z to the n minus 1 plus all the way up to a1z plus a0. This is our equation number 4. See that this definition makes sense because according to the assumption, there is no root of this equation lying in the unit ball B2. Okay? So that the right hand side of equation 4 is never 0. That is the reason the image of K is always in the punctured plane. Okay? Alright. Now, let H be the restriction of K to S1. Let H be the restriction of K to S1. That is, H is defined to be equal to the restriction of K to S1. Okay. So in other words, H is extended to the continuous map K. In other words, H extends to a map K from B2 to the punctured plane, right? So by lemma 2, the map H is null homotopic. So by lemma 2, H is null homotopic. Okay, so far so good. We proved that H is null homotopic. Now we shall now define a homotopy between H and the map G defined in step 2. We now define a homotopy F between H and the map G defined in step 2. Okay, good. So F is a map from S1 cross I to the punctured plane in dimension 2, given by, this is what we are defining, f of z comma t, where z takes value in the unit circle and t takes value in the unit interval. This is going to be equal to z to the n plus t times a n minus 1 z to the n minus 1 plus all the way up to a0. This is our equation number 5. Okay, so we need to check that f of z comma t is always non-zero. Okay, let's see how we can prove this. Observe that the mod of f of z comma t is greater than or equal to mod of z to the n minus mod of t times a n minus 1 z to the n minus 1 plus all the way up to a0. Okay, this is equation number 6. Okay, so how do we get to equation number 6? Follows from the familiar inequality from complex analysis, given by mod of z1 minus z2 is greater than or equal to mod of the following expression, mod of z1 minus mod of z2. Okay, this is one thing, and the other one is trivial. Mod of z is always greater than or equal to z, follows from the definition of mod z. Okay, so together they mean that mod of z1 minus z2 is greater than or equal to just mod of z1 minus mod of z2. Okay, so apply this here and we reach at equation number 6. Okay, good. Now, using triangle inequality, one finds that mod of t times a n minus 1 z to the n minus 1 plus all the way up to a0, this expression on the right hand side. Okay, this summand, we're taking this summand, and this guy is less than or equal to t times mod of a n minus 1 z to the n minus 1 plus all the way up to mod of a0. Okay, for given t in the unit interval. Okay, which means that now we multiply both sides of this equation by minus 1 so that the inequality reverses, right? So minus mod of t times a n minus 1 z to the n minus 1 plus all the way up to a0, okay, is now greater than or equal to, instead of less than or equal to, minus t times mod of a n minus 1. So we use the fact that mod of z raised to any power is going to be equal to 1, since z is a point on the circle, on the unit circle. Okay, so that is the reason we're just writing it as mod of a n minus 1 plus all the way up to mod of a0. Okay, so let me write it here. Since mod of z to the n is equal to 1 for all n in the set of integers, okay, as z belongs to the unit circle. Okay, good. This is our equation number 7, right? Now, this is equation 6 and this is equation 7. 6 and 7 together imply that mod of f of z comma t is greater than or equal to 1 minus t of t times mod of this guy, right? Mod of a n minus 1 plus all the way up to mod of a0. This is equation number 8. Okay, all right, so using 6 and 7 we reach 8. So I need some space. Let me erase this part. I don't need them anymore. Okay, now since t belongs to the unit interval and we are given the fact that mod of a n minus 1 plus all the way up to mod of a0 is less than, strictly less than 1, one must have t times mod of a n minus 1 plus all the way up to mod of a0 is strictly less than 1. Okay, okay, good. That is, so since this holds, in other words, we can write it as 1 minus t times this guy, 1 minus t times mod of a n minus 1 plus all the way up to plus mod of a0 is going to be strictly greater than 0, right? This is equation number 9. Okay, now 8 and 9 together imply the following. So let me write 9. 9 was 1 minus t times mod of a n minus 1 plus all the way up to mod of a0 is greater than 0. That's equation number 9. And this is equation number 8. Together they imply together imply that mod of f of z comma t is strictly greater than 0. This is equation number 10. Good. Hence, f of z comma t is never 0. Okay. So, indeed, the image of f lies in the punctured plane. Okay. Also verify that using the expression of f of z comma t, we can verify that f of z comma 0, if you plug in the value of t to be 0 in the expression of f of z comma t given by equation number 5, okay, which we erased, we can see that f of z comma 0 is equal to z to the n. The top degree term remains only because t is set to 0, and that is nothing but g of z. Okay? And one can also check that f of z comma 1, plug in the value 1 for t in the expression of f of z comma t, one sees that f of z comma 1 is equal to just the expression of the polynomial, given polynomial in z. Z to the n plus a n minus 1 times z to the n minus 1 plus all the way up to a0. Okay, and this is our h, okay, which is of course the restriction of k to the unit circle. Right. Alright, which means that f is indeed a homotopy between the map G and H, right? F is indeed a homotopy between G and H. Okay, good. But we have earlier shown that G is not null homotopic in step 2. We proved in step 2 that G is not null homotopic, right? And now that G and H are homotopic via this continuous map F, H is not null homotopic either. H is not null homotopic either, which contradicts that H is null homotopic as established earlier in step 3, which contradicts that H is null homotopic established earlier in step 3. Okay, so this is how we reach a contradiction. In other words, the polynomial equation x to the n plus a n minus 1 x to the n minus 1 plus all the way up to a1x plus a10 is equal to 0 has a solution in the unit ball. Has a solution in the unit ball B2 provided mod of an minus 1 plus all the way up to mod of a1 plus mod of a0 is bounded by 1. Okay, this is what we have proved in step 3, which is a special case of the fundamental theorem of algebra. Now the step 4, we prove fundamental theorem of algebra in full generality. Now we prove the general case. So we have a polynomial equation, x to the n plus an minus 1, x to the n minus 1, plus all the way up to a1x plus a0 is equal to 0, which is given by equation number 3. Okay, now choose a positive real number, okay, given by C, and substitute x equal to cy in the polynomial equation above here. In the polynomial equation above. Okay. So what do we find after doing that? We have cy to the n plus a n minus 1, cy to the n minus 1 plus all the way up to a1 cy plus a0 is equal to 0. Okay, so after dividing both sides by c to the n, we arrive at the following equation: y to the n plus a n minus 1 over c times y to the n minus 1 plus all the way up to a1 over c to the n minus 1 times y plus a0 over c to the n is equal to 0, which we number by 11. We can always do that since the real number c is chosen to be strictly positive, okay, which is not 0. Okay, good. This is equation number 11. So if the equation 11 can be shown to admit a root y is equal to y0, then the original polynomial equation equation number 3, okay, with which we started this fourth step, is easily seen to have a root given by x0 is equal to c times y0. Okay? Alright, so at this stage we do nothing. We just choose c large enough so that this holds. an minus 1 over c, the mod of this guy, plus all the way up to the mod of a1 over c to the n minus 1, plus the mod of a0 over c to the n. We want this sum to be dominated by 1. We can always do that by choosing c large enough. Okay. So this inequality is numbered 12. So now 11 together with 12 imply that the polynomial equation 11 has a root y0 in the unit ball V2. In the unit ball V2 by means of the arguments presented in step 3, right? And consequently, the original polynomial equation which we write again, which is equation number 3, x to the n plus a n minus 1 x to the n minus 4, all the way up to a1x plus a0 set to 0. This equation admits a solution given by x0 is equal to c times y0. Okay, QED. Okay, this completes the proof of the fundamental theorem of algebra. This is end of lecture 5. So I suggest that you read Bourse-Coulomb theorem, which is also an important application of what we have been doing so far. Read the Bourse-Coulomb theorem, where you will see that this theorem too, in the context of quotient topology that we discussed earlier in one of the previous segments, will prove handy to prove Bourse-Coulomb theorem again. Okay? So I suggest that you read it from page 357 of the same book by Montres. By Montres. Okay? Okay. Alright, so the next lecture will be on homology. So we'll be studying homology. Okay. And for homology, we are going to use the reference a basic course in algebraic topology by William S. Massey. Okay, so this is the end of the 5th lecture. Thank you all for attending this lecture.